In this video, we present our work accepted in ECCV animate your motion, turning still images into dynamic videos. Contextual video generation is not a new topic, and there are already quite some works in this field. For example, the trigger diffusion models, which can generate videos conditioned on both text and bounding box sequence, but it does not allow us to control the scenarios, so the scenario will be random. And the emu video models that is able to generate videos conditioned on text and first frames, but the motion of the objects are out of our control, so the object movement is random. And in this work, we aim to study the possibility of condition the video generations on text, first frame, and also the bounding box sequence. So the task setup is given a text description, an initial image, and a sequence of bounding boxes indicating object motions. The model has to generate videos that not only align with the text and the semantics of the first frame, but also ensure that the object's movement corresponds accurately to the provided bounding box sequence. On the left side, which shows an example of our results. The text is two fishes swimming in a tank. This slide presents our models. Our model is built up based on the pre-trained text-to-video generation models. We use the open source model scope T2V models. The right side of the slide shows our proposed modules to introduce the motion and image information to the models. To introduce the location information, we use the object-gated self-attentions. So in these modules, the input is the visual token and also the position tokens, which contains the location information and also the category embeddings. And we concatenate these two tokens, and then we do the self-attentions. And in the output, we only keep the visual tokens and we drop the position tokens. And additionally, we also introduce image-gated close attention and convolution layer with zero initialization to introduce the image information to the model. So we first use a VAE encoder to encode image to obtain the latent representation of the images. And in the convolution modules, we concatenate this latent representation with the diffusion network inputs. And in the get close attention modules, we use these latent image tokens to compute the key and value in the close attention layers. And we use the visual token to compute the query token, query, and we use this query key and value to do the close attentions. And in the output, we only keep the visual tokens. Our training pipeline has two stages. So in the first stage, we only train the object-gated self-attentions. And in the second stage, we fix the object-gated self-attention and we train the image-gated close attention, the first convolution layer, and also the temporal attention layer. Here presents our results. We compare our results with the model scope model and trigger diffusions. And this table, the first table shows that our model can achieve much better FBD values. In the second tables, we present the results of using different methods to introduce these conditional information. So this means we only use the first convolution layers. Concatenate means we use the methods similar to concatenate to introduce the first frame informations. And GCA means we only use the gated close attentions. And this slide shows that our methods combining the zero convolution layer and also the gated close attention layer can achieve much better FBD values. And here presents some results. This slide shows that our methods can generate videos which align best with the provided first frame text and also the bounding box sequence. We also find some failure cases. For example, our methods might ignore some small objects, and like the first and the second examples. And the second failure case is like some color of the objects might changes in the videos. Here's our conclusions. First, combining multiple condition signals is feasible, but it requires careful design and training scheme. And for future work, we should also consider the camera pose.